Okay, thank you all for coming today. Those of you who came. Those of you who did not come, we're sorry you're not here. But I'd like to introduce our speaker for the day. David Castle is a senior consultant at MarkLogic. He's been a professional software developer since 1996. And we will have a chance to talk with him more informally after the talk in the department library. So immediately after the talk, for those of you who'd like to find out more, we'll reconvene back in the department library.
I promise to hang out for as long as the beer and nachos held out.
You like, is cranberry juice and wheat thins okay?
We at least got the champagne, right?
Good, yes, of course, of course. Grad students, make sure you sign your name on the sheet that's on top of the podium there. A little bit more about David. David has focused on web development since 2007, I believe, according to his LinkedIn biography. Prior to that, he worked on desktop and server-side applications, including high-performance brokerage services, desktop information analysis tools, and information extraction. His experience includes working as a software engineer for Lockheed Martin, the founder and chief engineer at Community Trove LLC, and a senior programmer analyst at BNP Paribas Brokerage Services. Paribas Brokerage Services. So I turn over the microphone now to David. For anybody who's interested in databases, and I think we all should be, this will be a really interesting and illuminating talk. So take it away, David.
Thank you. First off, just to check, everybody hear me okay? Okay. So it's kind of funny, actually, that you mentioned we should be interested in databases, because I remember when I was an undergraduate here, I graduated from Villanova in '94. And when I was here, I looked at the databases class, and it's an elective course, and I thought to myself, that really doesn't sound very exciting. Nothing personal, Dr. Goldman. But I just thinking, you take your data, you put it into the database, you take it back out of the database, and then you go do something more interesting with it. That's the algorithm stuff, and that's where I want to be. And I maintained that attitude through undergrad and graduate school, and I always kind of took the approach to, well, when it comes time for me to find a job, I'll just find something that doesn't involve much in the way of that database stuff. And then I started working and found out that everything involves databases. So that was a good thing to learn, good lesson to learn, a little bit belatedly. See Dr. Goldman getting knowing glances at some of his students. So at that point, I said, okay, fine, I need to know about this stuff. I better learn some things, and started learning about relational databases, which was the thing to do because at the time, that was basically the only choice there was. This NoSQL thing has popped up relatively recently. But it does give me that much more satisfaction to come back here to Villanova and talk about databases, having come from that attitude when I was here as an undergrad. So it makes it a little more fun for me. So what we're going to talk about tonight, I'm going to take a look at starting off with why the NoSQL movement has popped up, what it is, what are the kinds of databases that are included in it and what makes them different from what we're used to. Going to look at some of the common aspects of databases where you may be familiar with the ACID properties of popular in relational database systems, and we'll look at how they're viewed in the NoSQL world. I am an employee of MarkLogic. Our database system is something that predates the NoSQL movement, so we don't tend to identify ourselves as a NoSQL database, but a lot of the attributes that we talk about in the NoSQL world apply to us as well. So it ends up being a good example to talk through, largely because I know it pretty well. Okay, so let's begin with the first question. Why did this come about? Because if we think about it, RDBMSs are quite familiar. There's something we've had a lot of time to get comfortable with. They are ubiquitous. Just about every database system out there, starting from about 10 years or so back, was a relational database system. And when you looked at projects that were being built, almost always your data was going to a relational database, because that's what there was to work with. And furthermore, as some of the professors here can attest, relational databases are backed by a substantial body of knowledge, by a body of research. So we know a lot about how these work, how to make them work well, both in theory and in practice, and yet we still end up wanting something different. So what is that? One thing about it has to do with structure. When you think about relational databases, you think rows and columns, right? And the essential notion of, that's the basic idea of when you think about how you're going to structure your data, what tables do I want? I'll have a bunch of rows. Each of those tables has different fields in it. I get rows and columns. Fact of the matter is that a lot of data does not fit neatly into rows and columns. Sometimes it's because it's more hierarchical in nature, sometimes for other reasons, but the estimates that my company has come across is that something like 70% of the data that the kinds of customers we pay attention to, their data just doesn't fit neatly into rows and columns, and that's often how they end up coming to us. Also, data changes. The structure of your data can change, and in the relational world where we need to define a schema and say, you know, we're expecting the data to have these fields and such like, it becomes a bit painful when that schema changes or when you introduce new data that doesn't fit into it. So even in the context of an individual project, we can have change that we need to be able to handle, and so a lot of the NoSQL databases are schema lists with the intention of making it easier to handle these flexible data formats. There's the round peg square hole kind of problem. So when we're putting data into a relational database, we have a certain structure. We pull it out. Let's say we're writing our program in Java, and now we're dealing with objects. There's an impedance mismatch between these two. And that mismatch can lead to a lot of work dealing with things that just shouldn't be hard anymore. And so with the NoSQL world, one of the ideas is to reduce that mismatch. For instance, a lot of the databases will store data in XML or JSON or something like that that's much closer to an object-oriented notion that we're used to. There's the aspect of FullText Search. If you've ever written a program where you want to be able to search through, I want to look for this word, and I don't care what field it appears in, if it's anywhere in there, I want to be able to find it. This is a non-trivial problem to solve. We'll talk about this in more detail later on. But again, this is another one of the problems that comes up. It's an itch that somebody needed to scratch. Yeah, we'll come back to that. And finally, there's the aspect of scaling. So a lot of these databases are intended to handle very, very large data sets. And when we talk about very large data sets, think about Twitter. Think about the Library of Congress. Think about PubMed. It's a set of articles that comes through. It's adding something like 5,000 new articles a week. I actually saw an interesting graphic recently showing, I wish actually I had captured it now. They showed the image data in the Library of Congress as a single pixel. And then they showed, I think it was Flickr, and then they showed Facebook. Just to give you an idea of the scale, the Library of Congress is small in the context of some of the current big data applications. Okay, so we're going to talk a bit about the horizontal nature of scaling that's made easier by the NoSQL approach. So I mentioned I work for this one company, and that company has kind of colored my view on what this term NoSQL means. So I figured I'd better go out and take a look and kind of broaden my definition. I'm not expecting you to read any or all of that. Just the point here is just that I looked in a few different places. I found a few different definitions, and they had quite a few different aspects to them. So I kind of pulled out the things that I saw were common, and some of this reflected what I already knew, and some of it was, you know, good stuff to add. Part of the NoSQL definition is really about what it's not. Right, so we've already talked about it's not relational. It's not just rows and columns. Most of the NoSQL databases, not surprisingly, do not use SQL for their interface language. It might be XQuery, it might be a JSON flavor kind of thing, something very much like JavaScript I've seen. But the idea is that this relational algebra, the SQL language sometimes makes it difficult to express what we're trying to do, again, depending on what we're trying to pull out. Excuse me, I get thirsty when I speak. So We're not using SQL for most of the time. We're not locking ourselves into fixed schemas. We're dealing with Webscale. I touched on that a little bit with the size of, for instance, Facebook, and Google is another example. And just think about these enterprise level things that are just dealing with massive levels of data. We see them in the commercial world, in publishers, in financial services. The unit that I work for deals with government agencies, and you can probably hazard to guess that they've got a bit of data going on too. And the lower right corner is we start talking about the ACID properties. It would not be accurate to say that ACID doesn't hold categorically. It would be accurate to say that many of the NoSQL databases choose to relax the ACID properties as a trade-off to get more performance. So as we look at this a little bit later, we're going to look at this idea that for most database systems, these 4 properties are considered to be kind of sacred. You know, you just have to have them. But as you think about it more, there are use cases where they're crucial, and there are use cases where they're really not that important. And so in the NoSQL world, many of the databases give us the choice of relaxing some of these properties in order to improve performance. Okay, the NoSQL world can be roughly categorized into about 4 different types of database systems. The first is a graph database. And the idea of a graph database, as you might imagine, is that it's storing basically a property graph. So we've got these nodes, and we've got edges coming out of them, and the edges may have some type or description attached to them. And so the astute observer will look at that and say, I can do that with a relational database. And you're right, you can, absolutely. We can set up tables that have the capture of the nodes. We can set up tables to capture the edges, and we can do this. The advantage comes in the way that the graph database does its storage kind of under the hood. It's focusing its optimizations on this particular class of problems. And if you think about that, you can think about the fact that, let's say, Oracle or MySQL or any of these, they're trying to optimize for a broad category of cases. It's a tough optimization problem if you think about it. Whereas if you say, this is the one and only kind of problem I want to solve, now you can get into something. You can really cut some corners here and there. You can make decisions that are focused on this and make it work out well. So what does it really do? When you get back a node from a graph edge database, what you're getting back is not just the node, but also all the edges that are attached to it. Those are all stored together so that you're getting them back as one chunk. Compare that to, in a relational model, we're going to do a lookup in a table for a node, and then we're going to have to do some kind of a join to get back the edges for that node. So we managed to save the join there. And there's also the matter of the schema. The graph databases that I found do allow you to set up new kinds of nodes very simply. And so these apparently work very well for the category of graph problems where you're dealing with local traversals. So we're not looking at the kind of problems where I'm going to work my way through a visit of every node in the database or every node in a graph, but rather I want to look at Dave and his connections on Facebook or something out to some degree, maybe shortest path between 2 things, but not exploring the entire graph. And for those cases, this works out really well. An example of this is the big data database. It's kind of an unfortunate name because big data these days is starting to mean something completely different. Well, anyway, it's meaning something different. But big data is a NoSQL database that's focused on RDF in particular. And it's designed to work really well on clusters of hundreds to thousands of servers. Okay. Another category we have is a very simple concept. It's the key value store. And if you ever have worked with hashes or associative arrays or whatever, in different programming languages, for instance, or maps they're sometimes called, then you know this concept already. It's very simple that we have some kind of a key, it's going to be a string, and we've got some kind of a value. And the value is going to be whatever. You know, it might be a simple scalar value, it might be something more complex. An example of one of these in action is actually one of the older things that I discussed in this talk, memcached. Memcached is basically an in-memory database intended to help you do caching much more simply. So as you're writing your application, you've got your full-fledged database where that's really responsible for storing information. You run some queries. As you store data, you just kind of stick that into this memcached key value table. And now you've got a really quick way to get that data back. So you can imagine as we're doing some session work, I hit a web page and it has to do some calculations to figure out some stuff about me. When my next request comes in, that data has already been loaded. It doesn't have to be retrieved from the database again or from the disk again. Okay. The downside to this kind of an approach, there are a couple. One is that it kind of limits the complexity of the queries, right? Because what we can do here is we can say, I want the server name value, and I get it back, and it is really, really fast at doing that. If you say, I'm really interested in pulling together let's see, I should have thought of a better example, but if I want to take a few of these values together and join them, then I'm not asking the database to do that. I'm doing it myself in the application logic. So I'm pulling back a set of values and then having to deal with them more manually. Likewise, there are no foreign key constraints. So I can't have something set up in here that says, if I put this value in, then it requires some aspect, something about another field. It's just not what this is intended to do. And likewise, no triggers. So I'm not going to be getting, post-update or post-delete or pre-delete kinds of triggers. A good balancing fact with that, okay, we can't do complex queries, which means we can't do slow queries either. Right? It's a key value store. This is order 1 to do a lookup. Basically, no matter how big it gets, we're just doing right into a hash table. So this is not going to slow you down, basically, no matter what you do with it. It's easy to distribute across a cluster. You can set up a few different machines that are each running memcached and stick your values in there, and you're off and running. Let's see. The parts in the values, sometimes I mentioned it will be simple scalar values, but imagine if the value in one of these things is a block of XML or JSON. If I do that, then all of a sudden I've got arbitrarily complex data available really quickly as a simple lookup. Now the example that I put up here, which I stole off of a Stack Exchange question, they've got an interesting approach to storing an object. You can see the top few values up there, user1923 underscore something. This is one approach to storing that kind of information. The other approach would be to say user1923, and then the value could be, again, an XML block, a JSON block, or some sort of object representation. Okay. A third category. There are these things called column stores. And so at first glance, you look at that quite reasonably and say, I recognize that. That's what I've been doing all my life. That's a relational database. Because after all, it's rows and columns. And to an extent, you'd be right. This is another one of those cases where it's a matter of the focus and the optimizations that are put in. So when we think about a relational database, the key unit of data is basically a row. That's what we tend to think about when we think about what am I getting back from the database. And so because our focus is on a row, the implementation of a database like that is going to be row-oriented. So on disk, I might have sequentially the ID field followed by the first name field, the last name field, the zip code field. Conversely, With a column store, I'm much more interested in a column, logically enough, to the point where the way we're storing information on the disk is, in fact, column focused, so that when I want to retrieve a column's worth of values, it's really, really fast. If I want to insert a column's worth of data, it's really, really fast. So again, this is one of those things where it's not solving a completely different problem than the databases we're used to. It's optimizing in a different way for a different category of problems. An example of a database that does this is HBase. Oh yeah, one of the neat notes I found is that nulls are stored for free because in a regular database that we're used to with the tables and columns, it does have to set aside just a little bit of space to say, by the way, there's nothing here, which takes up greater than 0 space. But storing that in a column store does not cost anything. Okay. Now we get on to the one I like most because I'm most familiar with it, and it's what I've been working with for the last few years at MarkLogic, which is a document store. So the notion of a document store is basically we've got some kind of an identifier. MarkLogic, we call it a URI. And then the value associated with that is going to be a full document. I suppose in some ways you might say this is kind of similar to the key value store where the value is large or complex. It's useful to point out here that the categories between these kinds of things are not hard and fast lines. They're not very rigid. So there are similarities between them, and that's fine. We do get more utility out of the document store, though. We can run much more complex queries. In this case, so the values I'm doing, I just have the beginnings of some XML, and we're going to fill that in a little bit to see what else we might put in there. But the takeaway here is that in a relational database where we're saying the core part of knowledge that we're interested in is likely to be a row from a table, in a document store, that core part of knowledge, core piece of knowledge, is going to be a document. Okay. So some of these use XML to store their data. Some of them use JSON. Some examples besides MarkLogic are MongoDB, CouchDB. Let's see. And a lot of the real-world data that the people are trying to solve problems with actually fits this model really well. So let's think about a database. Let's walk through a little exercise of how would we store some interesting data and make use of it. This is the shameless self-promotion portion of the talk. This is just a snapshot from my blog. So let's think about how we'd store this in a relational database. So we're going to have a posts table, most likely, and it's going to have a title. It's going to have some summary text, maybe. It'll have the full text of the article. This is a WordPress blog, so it allows tags and categories. So I'm probably going to have a separate table for the tags, and then that'll point back to my post table. Likewise, for the author, probably going to store that in a different place. So we'll have an author table that points back to the blog post. Let's see, and as well as let's say as a field for the published date. Okay, so now think about if I want to do a full-text search, looking for words like I want to find the word custom. All right, let's say the word facet if it's in the title, and I want to find the word search API anywhere in a post. So then what I need to do, I kind of have two choices. I can write code that says the places to look for text are in the title field, the text field, the summary field. Join up with the tags table so you can check any of those. Join up with the comments on this table. You get the point. This is getting kind of complicated. Another choice I have is to use another tool. I could bring Lucene into the picture here. And Apache Lucene is a tool that you basically point it at your database and work some magic, and it will index the content of your database so that you now have a simple-to-use word query in place. This is basically the approach that Google uses, very, very simplified, obviously. But they take the content. They say, all right, the word "the" appears here. So I'm going to add to my the listing of here's a URI where that word occurs. Take that scenario, and now let's say I want to add another feature. My grammar is sometimes slightly off, so I'm going to have an editor work with me. So I want to have editor comments available as part of my blog posts. OK, well, now that means I've got another table to join in. So am I going to pull that into my complex query and add the field to that? Or am I going to work with the configuration of Lucene and get it? Either way, I bring something in, and I'm having to make some changes there. Let's see. If we store it in a document store, we're going to take a different approach. So this is an example of how I might choose to store my blog post if I were doing it with XML. So I've got my metadata section, title, author, that sort of thing. You know, something interesting to note here. In a relational database, one of the key things we talk about is normalization. Right? And so we're interested in taking stuff that's going to appear in more than one place and put that somewhere else, so that then if we need to make an update, we update it one place and we're done. A common approach in the NoSQL world is to say, we're going to step back a little bit on the normalization bit. We're going to take the stuff that makes sense to have it with the document. We're just going to go ahead and put it right into the document, as opposed to having an ID here. So for instance, if I go searching for documents that involve the word castle, I've got the name right here. Now, I might still choose to have another document somewhere else that describes more information about me. I mean, as I'm sure you all know, blogging is the key to quick fame and fortune and riches. So I might have a document somewhere else that's got my bank account, deposit information, that sort of thing. But that's not stuff I want to search against, so I'll have that somewhere else. Likewise with the tags, the text of the tags is right here, and so it's available for a quick and easy search. We're going to see in a few minutes some reasons why that's a big advantage. The point about the denormalization is an interesting one, though, because on the one hand, it does give us the ability to search for the full text here. On the other hand, it does mean we do have information in different places, so I need some way to link that up. Now, what I might have done here, if I do have another document that describes the author and has more information about the author, I can always throw an ID tag or something like that on the author element up here, making it easy to link my way over to that other document. Some of the NoSQL databases, including MarkLogic, do have the ability to do joins. It's not something that's emphasized. We don't tend to do it nearly as often as we do in the relational world. In the relational world, if you're doing a database, it's almost certain you're going to end up doing joins just by the nature of how we design our tables. Okay. So if you think through the earlier approach with the relational system of how we might do the search across all these different fields, it's getting kind of complex. But if we take a look at this, the part on the left is how I might write a query in MarkLogic. This is xquery is the language here. So what this search is expressing is I want to look for blog posts. I want them to have the word facet, and I want the phrase search API to be within 10 words of the word custom. So that's a fairly complex bit of searching there, but I'm able to express that nice and succinctly, because you'll notice I'm not having to get into the details of what fields to look in. I do have the option to say, I'm only interested in this word if it's in the title. I can do that. I didn't in this case. The example in the lower right corner is one I borrowed from MongoDB's documentation, where they're doing a search against the name field, looking for documents that have the word Mongo in that name field. They store their data as JSON, and the code there looks very JavaScript-ish. Okay. So let's talk about scaling. So if we go back a ways, the common approach to scaling your database server when you got too much to fit in was to scale up. So we've got some server, and we've got all this stuff in there, and then, oh hey, that's not big enough anymore. We need to be able to store more than this thing can handle. What you do is you go out to Best Buy or wherever, and you buy a bigger server. More RAM, more CPUs, more hard drive. That works great until you need to go bigger, and then you need to buy yet a bigger server. As you can imagine, you get into some practical limits with this fairly quickly. The other approach is to scale out. So instead of buying bigger servers, we're just going to say, I've got one, I'm going to buy another one, and as many more as you need. You can do this with the relational model through techniques called sharding. The idea of sharding is you look at your data and you say, let's say any data from that maybe hashes to some value range, or all the posts written by a particular author or something like that, they'll go to this server, and then some other ones will go to this server, and you spread it around kind of manually that way in your application. A lot of the NoSQL databases are built from the ground up with the intention of making this problem really, really easy, so that at the application level you don't have to worry about it. So let's take a look at how that impacts us. So we start off with the database, and we grow and we grow and we grow and we grow. Next thing you know, we've got a cluster of databases, a whole bunch of them sitting there holding data. And when we're doing a search, the data that we're looking for could be in any one of these. And the tricky thing is, in a relational model, how do you arrange it so that there's some what's the word? There's a word for this, and I can't think of it. But you want the data that you want to use together, you'd like it to kind of be together, so that you're not having to look all over the place to make these. Sorry?
Locality of reference.
Thank you. Locality of reference. Thank you. But let's take a look at what might happen with the sharding approach. Let's suppose that the documents we're looking for as we issue our query, they're spread out among a few different servers. And let's say also that the tags that would help us find our stuff are spread out across a couple different servers, and maybe the author that we're looking at his information is stored on a different server. So you can imagine a problem now. None of these servers can look at just the data that it has and say, I have at least part of your answer for you. I know that this document is one of the things you're looking for. Here it is. Instead, what they can do is say, I've got a part of the solution, or what part of might be a solution. I found a tag that matches what you're looking for, so let me hand that back, and then that's going to have to be looked at some more to see whether that connects to documents that are of interest. Conversely, in the NoSQL world, we're looking at a full document is one piece of data. So when we look at what's inside of one of these servers, we're seeing a whole bunch of documents. So when I do my search for facet and custom and search API and stuff like that, each of these nodes up here can take a look and say, of the documents that I have, this one and this one, yeah, they match your query, here you go. So it simplifies the problem, and by letting each piece do a more complete job, and that ends up running faster. So a common aspect of how these NoSQL databases work is the idea of the shared nothing architecture. The individual pieces are isolated as much as possible from each other. So for instance, the indexes in a MarkLogic database are also broken down into the individual servers so that it can use indexes, it can use the full text. It's got everything it needs on there to decide which one of my documents match the query. And then some other machine can decide, well, I've got 15 responses, I only want 10, so I'll take whichever ones have the highest score. Okay. Okay. Let's think about the schemas for a little bit. So let's suppose that we are a publishing company, and we've got a bunch of data, books that you find people have all published, and We've got those in our database. We've got our nice schema set up, and all's well. Until the day we buy this other little publishing company, and they've got all their stuff in their database with their schemas, and now I want to take their data and bring it into my database. What do you suppose are the odds that their schema is going to match my schema? I'd say it's approaching 0, right? So I end up with a couple of choices here. I can try to map from their schema, just do an ETL enter, load, and transfer, or transfer and load, where I can basically take a look at each one of these fields and say, I think this maps to this field over here. And hopefully that works. Maybe it does. Odds are there's going to be some things that just don't fit very well. It might be as simple as I've got a given name and surname field, and they've got a name field. So now I have to figure out how to split those. That's a simple example. So one of the nice things about a Schema List database, something that does not impose a structure or care about a structure for that matter, is that when you can bring that data in right away. Are you done? No. It's not quite that simple. It's not that good. But if I take the data in this other schema and bring it into my, say, my document store database that has no schema and doesn't care about it, I do have FullText Search right away. I don't have to do anything special to now be able to do queries and get back information about your stuff. Now, I'm probably going to need to do a little work on the display because, after all, the structure of your stuff is different, and so maybe my presentation logic is looking for particular elements in the XML, and they're not there because they're called something else. So it's not that there's no effort, but you get much farther before you get into the work you're going to need to do. All right, so the obvious question that comes up. We've talked about things that are different, and in some ways, so we've talked about ways that some of these NoSQL approaches are more optimized on very particular problems. Does it help? That's what decision makers want to know, right? It's going to save me time, get me to market faster, and is it going to either save me money or earn me some money? Because if it's not, you're not going to have much of a case to work with it. So the answer that we found is yes, as you might have guessed from the fact that I'm still employed at that company. And the fact that I think one telling answer to this question is the fact that if you look at Facebook and Google and Twitter and these other companies, they tried the relational model, and they put in the effort and resources to come up with something completely new, build it out, release it to the world, happily, so it's open source and we get to play with it. But when companies like that are saying, this isn't working for us, we need something new, they're not doing it just for fun. They're doing it because it's helping with one or both of these criteria. So a couple examples, I just got to go to a tech conference for my company last week or the week before, and I heard a couple of neat examples that I wanted to share. One is that we had a customer that spent, this is a financial services customer, they'd spent millions of pounds trying to solve their problem with the relational model. The very large 800-pound gorilla of a company's database product. One of our sales engineers took what they'd been trying to do for a very long time in the relational world, rewrote it in 10 days with more functionality. We thought that was pretty cool. There was another example I heard about where this was a publishing company, and they had a process to change their application. And so the way it worked is, somebody wants a new feature on the system, they put in a request. 9 to 12 months later, they get their new feature. We heard that a lot of the times, by the time they got the new feature, they'd forgotten that they had asked for it. They used our system instead, and the amount of time necessary to add a feature dropped from 9 to 12 months to 4 to 6 weeks. So yes, it matters. It makes a big difference because We're removing the impedance mismatch. We're using software that is more focused on the problem that people are trying to solve. And the fact that we can get something that is a better tool for the job is what makes all the difference for us. The two things we see routinely in our customers is, one, they're dealing with big data problems, and two, they've tried the relational model and failed. And our customers are largely walking around picking up the scraps from what didn't work with other approaches. So, okay. I think I did something wrong with my fonts here, but whatever. So let's get into the ACID properties now. I imagine some of you are already familiar with these properties, maybe all of you, I'm not sure, but my intention is to kind of briefly go over what each of the properties refers to and then look at an example of a system that relaxes that property. First property we'll look at is atomicity, and this is the notion where we don't want only part of a transaction to stay, right? So it's either got to be the whole thing, all the updates you're trying to do in a transaction, or none of it. Think about the case where I'm paying my credit card bill. And so the first part of the transaction is the money comes out of my bank account, and the second part of the transaction is it goes into my credit card company's bank account. If both of those things happen, great. If neither one of those happens, okay, that's an error, but nobody's lost money and we're still okay. So we can work with that. If money comes out of my bank account and doesn't show up at the credit card company, I'm not very happy about this because now they're still asking me for money, but I'm poor. If money doesn't come out of my bank account but does show up in the other account, then that doesn't sound so bad actually. But so 3 out of 4 anyway. You know, we've got a problem. Excuse me. So an example of where this gets relaxed is MongoDB. This is one of the document stores that I mentioned earlier. And the way they enforce atomicity is to say, your transaction, you can do as many updates as you want to one document. But the moment you want to touch a second document, you first have to commit your first transaction and then start a second one. Okay, so why do they do this? The reason is, again, we're looking at systems that are intended to run on large clusters of databases. So let's consider a case where, where I want to make updates to that document that's on one server and this other document that's on some other server. Now I've got to deal with distributed transactions and distributed locks, and that's much more expensive than just being able to say, I'm going to deal with this one, finish, now I'm going to deal with this one. Part of the reason those are expensive is we need to worry about the possibility of deadlocks if we're doing multiple transactions, right? So if I have 2 processes, one that says I want document A and then document B, and the other says I want document B and then document A, it's easy to picture a situation where we get a deadlock. Each one gets the first document that they wanted and sits there waiting for the other one. And so we end up needing to build in something that kind of keeps an eye out for those deadlocks and will eventually blast one of them so that the other can finish. So MongoDB avoids all that by just saying you're limited to one, and if that's not good enough, then do something else. You can use a different system or whatever, but that's the limitation they put in. And as a result, they've been able to put together some really good performance numbers. Okay, another principle. I didn't do my graphics right here. So another principle is consistency, and the idea here is that system rules need to be enforced in your database. So common examples that we're familiar with in the relational world is that if I say that this field here can't be null, and then I try to insert a null, then that's an error. Likewise, if I designate some field as being a unique primary key, then I'm not allowed to insert 2 records that have the same key. Similar to that, in a document store, I might have a consistency principle that says for a given identifier, there can only be 1 document. You can't have 2 that have the same identifier. Excuse me. There's a NoSQL database called Cassandra that was put out by Facebook. that uses, it's called eventual consistency. So they're doing replication in their cluster, and as part of their replication strategy, they're saying, when I do an update here, it's eventually going to propagate out to everywhere else. They could have said, using the full strong consistency principle, they could have said that this transaction is not complete until it's been replicated in every place where it might be read. But again, they made the decision that that's not necessary for our use case. So instead, they're saying, we're gonna let you finish the transaction here, knowing that it'll get replicated elsewhere, and when it does, it does. And if you do a read that doesn't happen to be the current information, so be it. It's Facebook. It's not the end of the world. I forgot to mention earlier some of the different use cases, just to put the thought in your mind about, you can imagine the difference between a banking transaction, where these 4 principles are going to be very, very important, versus Twitter. What's the worst case scenario if Twitter loses some data, let's say a few seconds worth of data, or loses your tweet about what you had for lunch or whatever? Life goes on. You know, not to say that it's not important stuff that you're sharing and all that, but there are different levels of importance to individual pieces of data, and the idea of relaxing these ACID principles reflects that notion. Excuse me. Let's see. Okay. Third principle is isolation. So this has to do with, as we're doing a write, I might have a process that's going to do a transaction that's going to take some time. And maybe early in the transaction, I'm going to do a write, and later on in the transaction, I'm going to do a write. And the question is, what happens in between when somebody else does a read? So for instance, with my editing example, I might have somebody, as they're doing some editing work, they might make a change or make a comment on something, and that gets put into the database, but maybe we don't actually record who the editor was until later. So with the isolation principle, we would not want that to be visible. We would not want those first comments to be visible until the whole thing was done and the editor was in there as well. There are a couple different categories of errors we can see here. There are dirty reads, which is the idea that the first process does a write but doesn't commit it yet, and the second process does a read and sees that change. Now, process 1 hasn't committed yet, and in fact might roll it back later on. And so this is really not good data, and process 2 is seeing something bad there. There are non-repeatable reads where process 2 reads a particular record, and then process 1 updates that particular record, and then if process 2 repeats the read, they might see different data. That would be a violation of the isolation principle. And finally, there are the phantom reads where process 2 does a select, give me back a bunch of data. Might be in a relational world, I'm getting back a set of rows. In the document store, it might be a set of documents. And then if process 1 doesn't insert and process 2 repeats its select, then I've done 2 different reads and I got back different numbers of things, which is a problem. So the way MarkLogic handles this, as I believe a lot of the other major vendors do, is with multi-version concurrency control, which basically means we put a timestamp on our data so that we know when this was valid and when it wasn't, and that does a really nice job of solving the problem. I looked around for a while for an example of a NoSQL database that relaxed this property, and I actually could not find one. So I'm not going to say there isn't one. I'll just say that I couldn't find one. So perhaps this one's considered a little more important than the others. And then there's the notion of durability, the fourth of the principles. So in a nutshell, once a transaction is committed, it will endure. It's going to stay there, and nothing that happens is going to make it go away, not even if you kick out the power cord. Anything up until that commit, yeah, that's still vulnerable, but once that happens, you're good. And actually, it's interesting. Well, so the example that I found of this one, I'm turning to MongoDB yet again, they have an option where you can either relax this principle or not, and by default it is relaxed, such that it keeps a running 60-second log of what's happened in terms of updates, and then it flushes that every 60 seconds. So you can imagine if somebody kicks out the power cord, you could lose up to a minute's worth of your data, worth of changes to your data. It's potentially a problem. Actually, just yesterday, I saw somebody posted a link onto Y Combinator News, basically lambasting Mongo in particular for a big data loss. And then, so there's this whole big discussion, and somebody later came back on and said, oh, just kidding, it was just a hoax, and I'm just trying to teach you all to do your research before you pay attention to what you read on the internet. It's kind of a bizarre discussion at this point, but so another example is, so takeaway, don't think that MongoDB is as bad as that link. We're not sure about it yet, but it does have this option to relax this principle deliberately if you so choose. What do you get for doing that? Well, you get to not have to worry and not have to wait for the disk writes. Right? So the fastest thing you can do outside of this is journaling, where you're not taking the time to fully update your indexes and all that other stuff on the disk, but you are writing to disk a little thing that says, here's a change, it needs to be made. So now if you get kicked out before, sometime between I wrote the journal and I finished updating things on disk, then when you come back up, it can read through the journal and say, oh, okay, here's some things I missed, let me apply those, and now I'm ready to go. Right, so. Okay, I like this graphic because of a phrase I heard some time ago, the one throat to choke. So when you're looking for support, that's what you want. I want, hey, fix my problem. So in the NoSQL world, the question of support is much like it is for the relational world. We have some open source projects that are just maintained by a community of fans, basically. We have some open source projects around which companies have grown up and are providing professional level support for them. And we have commercial vendors that are building and supporting their own product. So in this sense, it's actually quite similar to the real world. So we can, relational world. So we can make comparisons between things like MongoDB and HBase versus MySQL or Postgres. So where does MarkLogic fit? I mentioned that we kind of fit under the umbrella, but we're a little different in some ways. So we don't use SQL, but we do hold to the ACID properties. We do provide support. We do enterprise level amounts of data. We have deployed situations, customers who have deployed us with hundreds of terabytes of data. We've been working on the petabytes. I'm not sure if we're there yet or not. One neat thing is that a release that happened just earlier this month now has an express license that lets anybody who wants to, you can download MarkLogic and put it into production for free. There are limits on the amount of data. I think it's like 40 gigs or something like that. But I wouldn't be working there if I didn't think the system kicked butt. So I encourage you to take a look if you're interested. So the other side of the coin, are there any downsides to all this stuff? Because I've certainly seen that there are some advantages to the NoSQL world and projects that are using them, but there's always a give and take, right? So one of them is, this first one is really the double-edged sword part of this, that it's a good thing and a bad thing at exactly the same time. We have more variety. That's great. It means now instead of holding our hammer and looking for nails, we can pull up our whole toolbox and walk around looking for all kinds of problems. If you ever try to be a plumber with a hammer, you know it doesn't work very well. The downside to that is that as an architect, your job got harder. 10 years ago, when you're starting a project, something you didn't have to think about is what kind of database you're going to put your information in. It's going in a relational database. You might have questions about, are we going to do a commercial one, are we going to do an open source one, pick one. But the key technology is not a tough choice. Now, as an architect, there's a lot more you need to know because you need to be able to make decisions between all these different things and pick the one that hits this, where its sweet spot is your problem area. So a good and a bad together. On the maturity front, a lot of these databases are relatively young as compared to the relational model. That model's been with us for 30 years. We know how to administer it. We know how to develop for it. There are lots of people who have these skills. Conversely, in the NoSQL world, if you're looking to develop with HBase, Cassandra, MarkLogic, Mongo, any one of these, you're more likely to grow your own developers than you are to find them. And the tools that you're going to use for administering them they haven't been around for quite as long. So it takes a little getting used to, and the administrators who are going to work with it will have a little bit of learning to do. That can work out to a good thing, actually. So one of the things we've seen in a number of our deployments is that the number of administrators for a large cluster of databases, when we switched from a major relational vendor to us, we've seen it go from 4, 5, 6 full-time people to 1 part-timer, because in some cases these things are that much easier to administer. But they are still new, they are still different. You still have to learn how to manage them. We talked about the support. Like I said, this is basically the same as what we've had in the relational world, so not really a big change there. Okay. So, moral of the story. What we end up with by having all this is that, as I said, we no longer just have a hammer, we've got a whole toolbox. We're much more likely now to have a tool that specifically addresses the kind of problem that we're trying to solve. And we'll do that hopefully cheaply, hopefully quickly. But the important part is that we do have choices and we can find the right tool for the job. Some other thing I wanted to say about that. Oh yeah, just the last point that you might wonder, well, does this mean the end of the relational database world? Are we done with that and we've moved on to NoSQL? The answer is no. I've not heard anybody in the NoSQL arena saying, victory is here, we're going to knock those relational guys out. Individual companies we might want to work on, but as a model, it's still perfectly valid for a certain category of problems. I mentioned earlier that something like 70% of the data that we see is stuff that does not fit well into rows and columns. Well, if your data fits completely into that 30%, then it might be a good solution for you. We're not out to get rid of what was there. We're out to make sure that the right tools are there for whatever the problem is. Okay, and I'm going to stop with that.
Thank you very much. We have